is supposed to be 0. So, chapter 10. We're going to do, there's only 4 sections in chapter 10. And we'll do 2 sections in each assignment. So we just have 2 assignments, today's. And then when you get on Tuesday next week, you can see the plan, take your test the following week on Wednesday. Alright, so chapter 10, still on series, and it's entitled Power Series. We are now finally going to attempt to answer the question, why? Why? Why are we doing this series, infinite series stuff? What good is it? How would you ever use it in the real world? What's the purpose for? Okay? So that's our goal here, to try to accomplish that. And in order to be able to do that, we want to start out with this conversation of power series. The whole chapter is on power series. We're going to talk about 10.1 and 10.2 today. We're going to kind of go back and forth and blur them together, so it's not really defined with this one and then that one. But the very first thing we want to talk about is, well, what is a power series? Basically, a power series is a series with a variable. And by that we mean x. Okay, so you will now have a variable in your series. So it'll be like a function, basically. Here's an example of what one looks like. So let's take the series, starting at 0 to infinity, of 6x to the n. Now, first of all, what kind of series is that? What'd you say? Geometric, right? Yeah, geometric. This x value is just your r value, your ratio. If we start plugging in values for n, we put 0 in first. Well, x to the 0 is 1, so we get 6 for our first term, which makes sense because that's what that 6 is. It's the 0 term. Plus, now we put in 1, and we're going to get 6x plus, put in 2, 6x squared plus 6x cubed, and so on. This is a power series. That's the formula for the power series. These would be the terms, the starting terms in the power series. You notice what I mean by the variable x. We've had an n or a k all along, but those have not been variables. Those are just the counters. Just told you what term number that you were on and what value to put into them to establish what the terms were. But now we have this unknown value. Since it's a geometric series, we could find the sum if it converges. What would have to be true in order for this thing to converge? So go.
X is greater than 1.
Careful, we don't want x to be greater than 1, because then they would be getting bigger and bigger, right?
Less than.
Less than 1. So if x was less than 1, this converged, and we could find the sum. What would the formula be? In other words, what would the sum equal? So let's just assume for right now, for the sake of doing this, that x is less than 1. And we know this is going to converge, and we're going to get an answer. If I keep adding up these values, I would get an answer. I don't know what x is, but I can still use the formula. So the formula for a sum, Corey used it over there.
1 over, or a over 1 minus.
You bet. And what's a for this problem?
6.
6. It's my 0 term. Over 1 minus, and my r value is? X. All of this, all of these infinite terms, if I added them up, I would get this equation right here. This function. 6 over 1 minus x. In other words, if you think of it as a function, because it is an unknown value here, if we said f of x is equal to this equation, so if if you were sitting in Algebra 2 class right now, I said, hey, look at f of x, there it is. That function is equivalent, we know, to this power series. This infinite power series. They're equivalent. So, in other words, if they said to you, hey, find f of 0.2, and again, they're only equivalent, remember, if x is less than 1 in this particular problem here. But if they said, hey, find f of 0.2, we could plug 0.2 into this equation. Or we could plug 0.2 into this equation. The power series. So go.
This is just kind of like basic algebra, but when you would have like 6 times 0.2 squared, do you only square 0.2 or do you square 6 times 0.2?
This exponent of 2 is only on this parentheses. Okay, so conceptually you get that so far. Does that make sense? Now, I know you're thinking, well, why in the world would you ever plug it into this one, the power series? That's crazy. Why wouldn't you just plug it into here? Right? But, what if your function is sine of x? How would you figure out sine of 0.2? Say it again, Natalie. You would plug it in your calculator, wouldn't you? Yeah. Well, how does your calculator find the answer? Does it like ask Siri, or does it like look it up in a special table in the back of the calculator?
Yeah.
I think it looks up in a special table.
You think there's like a special table in there for every
There's a
single
really small
possible
book back
number
there.
in the entire world, the infinite number of values that can be put in?
Like it's like a
It's like
0.3.
The writing is nanoscopic.
Do you ever stop and think about that for a moment? Here. Well, I'm going to tell you this. This is really going to shake your world. Every single function, every single one, can be written as a power series. Now, when I say everyone, there are a few exceptions to that. But for the most part, every single function can be written as a power series. Every one. So, your calculator doesn't have a magical list of sine values and cosine values and secant values and cosecant values and log values in the back of it. Your calculator, somebody, when they created the calculator and programmed it, so when you push the sine button, it enters the value into the power series that's equivalent to sine. Now, first of all, let's look at that. You can, well, let's write it down here for you. You're gonna, at some point you will memorize this, but I don't want to scare you too much right now. So, the function of sine of x is equivalent to the power series of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on.
It's just
Only odd
2
numbers.
from 1.
And
Pretty,
alternating.
it's just absolutely beautiful, isn't it? I mean, look at that. Just stop and think about that. Look at the pattern on that. Isn't that amazing? And I'm not saying that's approximately equal to sine. That's exactly equal to sine. Exactly.
Wow.
Now, if you were living in the 1700s and you wanted to find the sine of 0.2, until calculus came around, you would, what would you do? You have no idea what to do. But now, if we knew this power series, we could come up with a really good approximation by hand of the sine of 0.2, because calculators haven't been invented yet. And we would plug 0.2 into all my x values there. So f of 0.2, in other words, sine of 0.2, would just equal 0.2 minus 0.2 to the third over 3 factorial plus 0.2 to the fifth over 5 factorial, and so on.
Are we saying 0.2 radians?
Yeah, I'm saying radians. But it wouldn't matter, right? The calculator, as long as you have, the calculator would have to distinguish the difference between those two modes, and it would have, yeah.
So the sine, it's like the sine of 0.2 is the sum of the infinite series when you put 0.2 in for x.
Isn't that amazing? And that's the only way you can truly calculate the sine.
Sounds like a lot of work for the calculator.
Well, that was the cool thing about when they got computers and calculators, is like, holy cow, now we can do 1,000,000 terms in less than a fraction of a second and have a really good approximation. So when you plug sine of 0.2 in your calculator, you don't realize it, but your calculator is giving you an approximation. But it's carrying it up to so many terms that so quickly, it really doesn't matter at some point. Just like you did number 57 over there. It didn't matter. After 14, you keep plugging that in your calculator and adding it on, but it's not changing the value of it at all. Okay? And that's the only reason it came out exact there, is your calculator can't deal with it. That they're only going to be able to carry out so far, and it's going to have to stop. Every single function, your calculator would not work without power series, without infinite series, without this conceptual, strange theory that if you add up an infinite number of numbers, you will get an answer. And the only way that would work, remember, is this convergence. So the big question is, before I plug 0.2 in, I need to know, will it converge? And it's a power series. It has a variable x. So it's no longer a question of, does this series converge? Now the question is, for what values of x does the power series converge? What can I put in here and get an answer? That's the question you're going to be answering in chapter 10. Okay, so we're going to write that. This is the important statement. By the way, if you haven't kind of figured this out yet, when we say power series, think in your mind this infinite polynomial, because that's really what it is. So if you're having a hard time with this concept of power series, just think, look, this is just a polynomial. Got x's, they got exponents. I still think that's just amazing. Every time I look at the beauty of that pattern, the odd exponents, the alternating signs, the factorial on the bottom.
How did people figure it out?
You're going to learn the formula.
Yeah, how do
You're going to learn how to you will learn how to make a power series for every single function. Like you'll learn that on the next assignment. That's part of what you need to know for your test. Okay? So
They do struggle to memorize that question, but you wonder how they actually or is there more stuff like this that people have?
We wouldn't have coded this. We wouldn't have coded this. You'd have to do all the math in your head.
this is, what's exciting is this the timing. We're going to celebrate Pi Day on Tuesday, and it couldn't have been better timing here. Because you really, I don't know if we've had this conversation yet, but when you think about pi, did we talk about this?
Probably not.
How do you find pi? How is pi calculated?
Is that a power series?
Is that power series? Yeah, I was.
Well, it doesn't have to be, there isn't an unknown value, like you don't put, there's no x in pi, right? Pi is not a function, an equation. But it is an infinite series. I'll show you a little video on it. I mean, if you stop and think about it, everybody says, well, it's just circumference divided by diameter. Okay, well just wait a second. What kind of number is pi? Irrational. What is the definition of an irrational number? Well, the technical definition of a rational number is that you can write it as a fraction. So if it's irrational, you cannot write it as a fraction. You're like, wait a second. Isn't circumference divided by diameter a fraction?
Wow.
How in the world could you take two measurements, two finite values, two rational numbers, divide them and get an irrational number? You can't do that. And some people say, well, it's approximately 22 divided by 7. Okay, but that's an approximation. And some people, I just push pi on my calculator and it gives it to me. Well, what is your calculator doing? Did your calculator memorize 10,000 places of pi and just spits them back at you?
Yes. Yep. No.
No. Most likely not. E is the same way. Like when you plug e to the x on your calculator, it doesn't like store in its memory, oh, okay, 2.71, yada, yada, yada. It's a power series. The whole calculator is all based on series. Okay, so here's the big question from this chapter. For what values of x does the series converge? And by series we mean power series. And another way of asking this question is, what is the interval of convergence? Okay, so when we say for what values, we mean, okay, when you give us an answer, let's get this answer in terms of an interval. If we're going to be making power series for any function, we want to know, if we're going to put a value in for x, I got to know I'm going to get an answer. And the only way you're going to really get an answer when you add up an infinite number of numbers if it's convergent, if it converges. Okay, so we're going to go back to the one we just had here. This one, I think intuitively this will be pretty easy for you. So this is a geometric series. And you already answered my question. For what values of x will this converge? What does x have to be in order for it to converge? Okay, and it's absolute value, right? Absolute value has to be less than 1. So let's write it as an interval notation. We're going to talk about it being an interval. So from what to what? I'm so afraid to answer that question. It's the absolute value is less than 1. And back in 4th grade, you started, no, not 4th grade. 7th grade, you were all worked on solving absolute value equations. What could x be? The absolute value of x has to be less than 1. From?
0 to 1.
No.
Negative 1 to 1.
Yes, thank you.
All the absolute value.
Including the endpoints or not including the endpoints?
No.
Not. So around parentheses or square bracket?
Round.
Around parentheses. This is my interval notation. It can't be 1 or negative 1 because that would cause it to diverge. Okay? As long as you put a value in between there and there into that equation, you will get the same answer for the series as you would, for the power series as you would for the function of 1 or 6 over 1 minus x. Alright? This is your interval of convergence. By the way, I'm going to just write that down so you remember. Absolute, we got it because the absolute value of x had to be less than 1. Interval of convergence. Some other terms that come along with this idea of interval of convergence, they'll talk about the center. What's the center of this interval? 0. That's not so bad. So the center equals 0. It's just the middle of your interval. And then they'll talk about the radius. How far off from the center does it go? 1. So it's either side of 0, it goes out 1. That's the radius of the interval, or radius of convergence, or center of the interval of convergence. Okay? So if it's a geometric series, power series, it's that easy. And if it is geometric power series, just thank the math gods that it is a geometric power series, because that's easy. If it's not, it's a lot harder. So, as you can imagine, most of them will not be geometric. We've had all those other kinds of series. So, not geometric. Always use the ratio test. We haven't got to the hard stuff yet, so don't moan to determine the interval of convergence. So that's good news. It's not like you have to try different things. If it says find the interval of convergence, you look at it. If it's geometric, bam. If it's not, we're going to use a ratio test. You can also use the root test. That doesn't happen very often at all. Like if you did 1,000 problems, one might be a root test and the other 999 would be a ratio test. And the only way you recognize it is the whole thing is raised to the n power or the k power. Alright, so we're going to focus on the ratio test. Here is a good example. So, right away, how do I know I'm trying to find an interval? Well, let's say find the interval of convergence. How do I know this is a power series? Let's start with that question. There is an x in it. Okay? So you can see that variable is x. The n in this problem is not a variable, it's just a counter. Beautiful. So, we're going to set up the ratio test. We're going to take the limit. But before we do that, right away you should recognize, before we get too far down this problem here, you can immediately tell from the given problem what the center is. It's always the x, so that you'll recognize the center because it's x minus the center. Whenever you're given a problem, the center is always being subtracted from the x value. So in this case, the center is 5. What if this parentheses had x plus 1? What would the center be? Negative 1. What if there wasn't anything here, it was just x to the n? What would the center be? 0. Okay, so that's easy. You can immediately find the center. So we kind of have a good idea. Now we know right where the middle of our interval is. We just need to know how far from each side to go. So we're trying to find that radius. Alright, so here we go. Stay awake. We've got a lot to cover in this one problem. So, ratio test is the absolute value. We're going to add 1 to all of our n's. So we have n plus 1 here, and 3 to the n plus 1, x minus 5 to the n plus 1. So we took our original equation, added 1 to all of the n values, and now we're going to multiply it by the reciprocal of our original equation. So we're going to get 3 to the n here, and we're going to get n down here, and x minus 5 to the n here. Now, problems that weren't power series, we would keep going and see if we get an answer. And how did we know from our answer if it converged for the ratio test? You know, there's so much to keep straight. And what do you remember? Ratio test. How do you remember? Less than 1. We want this to converge. So we're going to say this is going to be less than 1. And now we're going to work backwards and solve for x to find out what it would take for this to be less than 1. You with me? Okay. We are actually, when we solve this, you got to know when to stop. And so I'm going to write a little note here so remember, we're going to solve until you get down to x minus the center value is less than, and then this value here will be the radius. Okay, so we're not going to go all the way down to x. We want to stop at the, in this case, x minus 5. That's where we want to stop. Once we get it down to there, then we'll know what the radius is. Because after all, x minus 5 absolute value, that's how you, when you find out how far away something is, you just subtract the two quantities. And if you take the absolute value, it doesn't matter which way you subtract. So by taking x minus the center, I'm finding out how far away from the center my end of my interval is. That's what this is. It's just a length here. That's all we're doing. Okay? All right, now the fun part. Here we go. We start canceling. So we have n plus 1. That doesn't do anything. 3, n plus 1 here. So that's going to be canceling. Oh, I should not change the color like that. To just have a 3 in the bottom. This x minus 5 to the n cancels with almost all those except for 1, and you're left with that there. We're going to rewrite this. We're going to have the limit n approaches infinity, absolute value, come on, n plus 1, x minus 5, 3n. Any questions so far? Not too bad, right? I don't know why I was trying to scare you. This stuff's easy. So, we take the limit. Now, notice, it says n approaches infinity, not as x approaches infinity. This stuff, x minus 5, we want left in our answer. We're not dealing with this x minus 5 stuff. We're trying to take the limit of all this n stuff over here. So just focus on that when you take the limit. You're going to use L'Hopital's rule, and what will you eventually get for the limit?
1/3.
You bet. And then we're done. So that limit, absolute value, 1/3 times x minus 5, parentheses, is less than 1. I want to solve that. Well, the 1/3 is just a positive number. I can take it out front. And I get 1/3 out front there. How am I going to get rid of the 1/3? Because I don't want it there. I want just x minus 5. You bet. So now we're going to get this. And we stop. We're very excited. We can tell the interval because we know our center was 5. And we know now, what is the radius? 3. So the middle's 5. We're going to add 3 and subtract 3. Add 3, we're going to get 8. Subtract 3, and we're going to get 2. Our interval's from 2 to 8. So far, so good. We're right up to that point. Be prepared to moan. What about the endpoints?
Squares.
You don't know. You have to check and test them. We need to see what's going on exactly at 2 and 8. So we're going to plug them into the original equation one at a time and test that series. And we're going to use one of our 10 tests for each one of those endpoints to see if it converges or diverges. The whole point of you learning last chapter 9 was for this right here, to check to see if these endpoints are converging or diverging. Well, we shouldn't say the whole point, but all of that is going to help you be able to answer that question. Okay? So, right down here, check endpoints. And we're going to let x equal 2 and x equals 8 in the original series. And I'm going to go to, oops, 2 dots and an I there. I'm going to go to a new page. It's going to take a while. I might run out of room on this one. You ready to move on to that? Can I? Okay. So, let's start with the 2. So we write down let x equal 2. We put 2 into the original series. So we had the summation n equals 1 to infinity of n over 3 to the n, 2 minus 5 to the n. And now you want to simplify and simplify and simplify before you start trying to do any kind of test on it. So 2 minus 5 is negative 3. So this is equal to n over 3 to the n, negative 3 to the n. Would I ever stop there? No. We know that you don't stop. If you have a negative 3 or any number to the n power, you've got to get that negative 1 out of there. So this negative 1, or negative 3 to the n, is the same as negative 1 times 3 to the n, which is the same as negative 1 to the n times 3 to the n. Okay, we did that, right? Alright, that should have come up. Alright, so that means we have now n over 3 to the n times negative 1 to the n, 3 to the n. Keep on simplifying, and these 3 to the n's will cancel. So now we have this. And there isn't any more simplifying I can do. So now I reach into my bag of tricks of evaluating series, and which one would I use for this? Alternating. This is an alternating series. I'm going to take the limit of this, cover up the negative 1 to the n, take the limit as n approaches infinity of n and get infinity. What does that tell me? It does diverge. This diverges by which test, though? Nth term test. Because he realized, oh shoot, we should have done the nth term test first. We would have just taken the limit as n approaches infinity of that original thing. He would have approached infinity, and that would have meant it diverged. Okay, so we got the 2 done. Square bracket around parenthesis. Well, it diverged. Do we want to include 2 in our interval? No, we don't. It does not converge at 2, so we want around parenthesis right now. Now let's check out the 8. So these problems are like 3 of the old problems in 1. You got the original series to do the ratio test on, and then you have each endpoint that you have to do a test on with different tests. So let x equal 8. Then we got the series 1 to infinity, n over 3 to the n, 8 minus 5 to the n. Well, that works out beautifully because we have now n over 3 to the n times 3 to the n, and you just get n. What will that do? What test are you going to do on that? You bet. So you can see right away we take the limit as n approaches infinity and get infinity. This diverges by the nth term test. So our interval is not including 2, not including 8, but 2 to 8. That is your interval of convergence. What is the cent? This is the interval of convergence. One more time. The center is 5. The radius is 3. That doesn't change by the endpoints. That's still the same. So, it's just, there's a lot of work, obviously. That makes sense? Hopefully, you will in practice. Okay, when you do the ratio test to find the interval of convergence, there are a couple times you get some unique answers. So we're going to say here, unique intervals of convergence. Alright, so you're going to, you got the ratio test going along here, yada, 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 and you do all the work, and you get down, and let's say it was centered at 3, so you have x minus 3 here, and you're trying to get things worked out. And when you take the limit, you end up getting infinity in there. That's weird. And then he stopped and think about it. You don't want to divide by infinity. I guess you could. That's an interesting way of thinking about it too. What can you plug in for x that will cause that to be less than 1? Hold on to that thought. That's an interesting thought. Is there anything else besides 3 at all you think that could possibly get that to be less than 1? Infinity times a number, will that be less than 1? Come on, people, right? No. Is there anything you put in there? No. There aren't any values at all. Except, at a minimum, every power series will converge at its center. Every one. Because, if you think about it, let's say this worked out to be this. So if I knew the power series was like 1, and then x minus 3 to the first, x minus 3 to the second, x minus 3 to the third, and so on. And I want to know what values can I plug into that and get an answer. There's always one value. It's always the centered value for sure. So in this case, like Segal said, if you put 3 into there, those would all be 0, and you would have that, whatever that leading term is that doesn't have one in it. And if there wasn't one there, the answer would be 0. Okay? So, this converges at x equals 3. So, every power series converges at its center. Okay, at a minimum. So, the bottom line is, if you get this wacky answer with infinity in here, then just stop. And the answer is, it only converges at whatever the center is, in this case 3. There's not an interval, it's just at that one number, and that's it. That's the only value that will work there. So that's one unique kind of situation. And guess the other unique situation when you do all the work here.
If it's something over infinity, like infinity's in the denominator.
Yeah, and so what does that equal? What is a number over infinity? So let's say you get 0 there for the limit. What can you put in for x, times it by 0, and have it be less than 1? Any number, right? So these are nice. Boy, again, thank the math gods if you get one of these. Because what is the answer? What's the interval? If it's everything. All reals, otherwise known as? An interval notation would be? Square or round, is that right?
Can't you just like choose?
You cannot just choose. Can it equal infinity? No, it has to be round, right? Infinity would never be square. That means you could actually put, you can never equal that number. So this is all reals. So that's nice. You have to check the endpoints, in other words. No, you don't have to check the endpoints here, and you don't have to check the endpoints there. That's great.
I love these.
So, if it's geometric, wonderful. If it ends up here, that saves you time. If not, you're in for the long haul there, going through all the work and making sure it works out. All right, here's your assignment.
Let's go on this assignment.
It's short assignment, means we have long problems, but that's better than having a lot of today.
Do you have any extra loose food?
Yeah.
Yeah, and I don't like it.
I mean, I should.
I always throw it short. I was like, I don't think it's
You're wearing,
And then it was
you have a jacket.
so I was like, What?
It's
It was
crazy
like
to take
60
that.
yesterday.
You go jacket too.
Run so fast. Natalie,
Well,
is
this is
it
very,
today?
a lot of even ones
Is
here.
it a
Uh-oh.
Tell 5.
That's all even numbers.
Oh my gosh.
Oh no.
I gotta give you something to complain about, otherwise you guys would never complain.
Yeah, I could do these all wrong, and
I
that's
kind of
just.
like that feeling. That way you don't get demoralized if you know that you did it.
Until you're here and you read some off and you're like, oh, there's another one that I got wrong.
No, then it stresses me out because I'm like, I gotta do this entire homework during class now because I got it wrong.
Gee.
Good thing I got thick skin.
We're just very pessimistic people.
Oh, what the heck?
Hey, it's a short assignment though, so.
Wait, you listen
I
to
doubt
point two
it's gonna be
first.
short.
Now, we're gonna talk about, I'll let you write those down, we're gonna look at each section and talk about the directions and make sure. You notice I put, kind of grouped it a little differently for you, but.
Even problems, you just do them, and you can only hope for the best.
Oh, relax. Or you can get them all done before you left here today.
You're severely underestimating
You
myself.
could always check with the answer book in the morning too. 688. Please turn to page 688.
I'll come in Saturday morning just to see my answers.
Bag of janitor to let you into his room.
Please, sir.
There aren't any janitors here on Saturday. There's more teachers than there be janitors, that's for sure.
Do you come here on the weekends?
Occasionally, yes.
Get away from the stress of home.
That and to correct my calc test, stats test, or
Wait, you can't
Yeah,
correct your
you gotta
stats
get
test
the
or your
plan
club test at your
back
house?
just
I usually do correct at home, but I can't do other stuff at home.
I don't like the cameras.
I'm not complaining, I'm just saying, yeah, occasionally I come in. I don't come in every weekend, but
We should come in this weekend and we could all come in and
Notation
have
by
a little
nine.
homework sesh on Saturday.
I wanted to explain that.
Oh, okay.
Are we ready? We're looking at page 688?
Thank you, Emily.
Yeah.
Okay, so 10, 12, all those, you'll notice where it says basic skills there. Does yours say basic skills?
Yeah,
Yeah,
yes,
okay.
That's
That's fine. So we're finding the interval of convergence. That's what you're doing, okay? All of these would require, all of these are not geometric, let me put it that way. All right? These two are in the same section. These are the only two that are geometric.
So we have 9 really long ones.
And I'm highlighting them to tell you they're geometric because you might look at it and not recognize that it's geometric. So for example, let's look at number 9. The very first one. 2x all to the k power. It may not look like it's geometric, but it is. What is the r value? 2x. Okay, 2x is the r value. So what has to be true about 2x? So the absolute value of 2x has to be less than 1. Maybe. Well, there it goes. So, how would you solve that? First of all, what is this centered at? Let me start there. 0. So we got to get down to just the x. How are you going to solve for just x?
Put the 2 outside.
You're going to divide by 2, right? Yeah, you could put the 2 outside and then divide by, if you want to take 2 steps to it, it's fine. But yeah, you're going to divide by 2, and you're going to get the absolute value of x is less than
Negative.
1/2. We're dividing by 2, 1/2. Okay. So, my center is 0. What's my radius? 1/2. What's my interval of convergence?
Negative 1/2.
That's it. We're done with that one. Those are beautiful. And I don't want to spoil it too much fun. And the other one you have, 17. But if you look at it, you should just recognize, it should be very obvious to you what the r value is there. Okay? Now, stop for a moment and let's go to page 677. So go back to stuff out of 10-1. 23, 25, and 27 you're doing on this page, 677. So, this is where you would use a power series to approximate. And yes, I get it. Why in the world would you use a power series to approximate the square root of 1 plus x? Because you could easily do that by hand. Although, again, the calculator, the square root of 1.05, I'm sure it doesn't have every single square root stored in its memory to recall it. There has to be a procedure your calculator is doing to do square roots. And it might be this one. Okay? Or something similar to that. So, they're giving you the power series up to a certain number of terms. Looks like 3 terms. You're going to use that, and that little 2, that piece of 2, that just means they stopped when n equals 2. So they're giving you the power series for now, asking you to plug a value in to the power series. So for 23, if the function is 1 plus x underneath the square root, and you're approximating the square root of 1.05, what would x equal? 0.05, right? Not 1.0, but 0.05. So all they're asking you to do is to take 0.05 and plug it into that power series and write down what you get. Then they want you to find the actual value on your calculator, the square root of 1.05 in this case, and subtract that from your approximation you just got to find out how far off you were, your error. That's it. So, those 3 problems will only take you a couple minutes, and the one that's left here will take you less than that. These will take you some time. So, whatever order you want to do them in is totally up to you. We do have 19 minutes, don't we? So, if I were you, I think I would start with these right here and knock off quite a few of those before you leave, just to make sure you're doing that stuff right. That's the hardest stuff.